All right, so as many of you know, I have a strong interest and preference for recorded lectures when there is theory involved. I became a big fan of these a few years ago, and those who have taken Astro with me know that that's what I do when possible. So this time I want to do the same. I'm going to be showing a few slides and notes from a class that I taught in the past about spacecraft attitude, dynamics, and control. So I'll go over attitude kinematics at a very high level, enough so that we understand the concepts and we can use them without digging too much into theoretical demonstrations unless we have to. Again, this is a class where you use knowledge rather than studying a single topic. If you need to go deeper, you can do it at any time, of course. But I want to cover attitude kinematics because it's one of those topics that, even though it's covered in dynamics, in robot geometry, and I think other classes, it's always source of confusion. So we're here trying to handle the geometry of rotations. And I always invite students to make the parallel in their minds with a particle. A particle in three-dimensional Euclidean space can be located by choosing a coordinate system, an origin, three directions that are usually orthonormal, and associating an x, y, and z variables to the position of the particle. And when someone gives you a velocity profile, then you know the differential equations that give you the kinematics of the particle are very simple. X dot equals v on the x-axis, and so on and so forth for y and z. Very simple linear differential equations that you can integrate in time, analytically or numerically, and reproduce the trajectory of the particle, which is x in time, y in time, and z in time. Now, this is the same for attitude, except there's nothing linear about attitude, and it's not so intuitive. What you try to do with attitude is look at an object. In this case, for us, it's the spacecraft that you approximate to a rigid body, and try to represent how its orientation changes with respect to another object, which in this case is the ECI, the Earth-centered inertial frame, which is not a physical object, but again, we know that a frame, go back to your dynamics classes, a reference frame is a collection of at least three non-collinear points whose mutual distances don't change with time. So if you have a frame, you choose one point fixed in a frame, three directions that are orthonormal, they are also fixed in the frame, and that's your coordinate system. That's another quite often topic for confusion. A reference frame is a collection of three non-collinear points whose mutual distances don't change with time. It's an object, it's a rigid body. A coordinate system is just your choice inside that frame of an origin and three directions so that you can have a ruler, you can measure things. So what we do for kinematics in general is we represent the geometry rotations. We try to track how something is changing in space, be it a particle or a rigid body, without knowing what is causing the motion. We don't study the causes of motion. That's dynamics. We care about representing the motion. And in our case, this is what we're trying to do. We're looking at an object, the spacecraft in this case. We attach an origin and three directions that are fixed in the object, the body axis, and we want to represent how in time these three directions change with respect to three other directions. Here I'm calling it FA, the frame A, which can be ECI, and I apologize if in these slides and the notes I'll change nomenclatures and names of things a few times back and forth. This is old material, but it still gets the point across, I believe. So you want to represent how these three directions are evolving in time somehow with some parameters. For a particle, you would choose X, Y, and Z usually. So we want to express the orientation of a frame with respect to another. Please follow my mouse if you can. We want to, once we're done that, we'll be able to transform vectors among different coordinate systems. What you do in kinematics is express the angular velocity as a function of orientation and time. We do not really care about the origins here. So I've had this question in the past and in several of the classes. When you talk about attitude, orientation of an object with respect to another, of a frame with respect to another, which boils down to two coordinate systems and how they project onto each other, you do not care about the origins. The spacecraft will never have the origin of its coordinate system corresponding to the origin of the coordinate system for ECI, otherwise it will be at the center of the Earth. So we do not care about that. And of course the numbering of these slides is absolutely incorrect, probably, but we'll see. I've removed some of the slides that we don't need. So you will see sometimes these notes appearing, and what that means is that I'm going to leave the slides, I'm going to exit that, and I will give you everything, and open this PDF, which are my handwritten notes, if I manage to move it to this screen. Yes, I may be able to do it, of course not. Let's see if it does it this time. Yes. This is not really lecture 4. Again, these are lectures from a longer class. We want to focus on what we need. Okay, so the unique and general way to represent the rotation of a frame with respect to another, how 3-axis basis is oriented with respect to another basis, is this DCM, direction cosine matrix or rotation matrix. So if someone asks you what is the most general way to represent an orientation of frame B with respect to A, you say you choose the coordinate systems for both frames, they remain fixed in those, and you use the DCM, which is the following. Well, before we define it, let's look at an example. You have a vector V in three-dimensional Euclidean space and a basis I, J, and K. V can be expressed the following way. It's norm times this unit vector, which is composed by the cosine of alpha 1 I plus cosine of alpha 2 J plus cosine of alpha 3 K, and I hope, again, you can follow my little hand here, which is my mouse. This alpha 1 is the angle between the vector V and the direction I. Alpha 2 is the angle between vector V and coordinate direction J, and the same for alpha 3 with K. And from Pythagoras' theorem, we know that this relationship holds. Of course, it has to hold because I have the magnitude up here, so this has to be a unit vector. Now, the same generalizes to 3 directions in space. Imagine this I prime, J prime, K prime just being your V, and for each of those you're gonna project onto I, J, and K. And so I prime is going to be some cosine of an angle I plus another cosine of another angle J plus another cosine of another angle K. You do that for J prime, you do that for K prime, and you get these 3 relationships that project the basis of this coordinate system that I'm calling F prime, and in a second I will start calling B. Project these unit vectors into these other unit vectors that are the basis for F that I'm going to start calling A. As I said, I switched language a few times here, and I'm sorry for that, but it should be not too hard to understand. So let's see. What we have here is now a bunch of numbers, these cosines. There are 9 of them, of course, and I call them C11, 12, 13, etc., etc. And so I can put them into a matrix, which is my direction cosine matrix or rotation matrix that goes from A to B. Because I go from A, if you want to look at things this way, you start from the right and go to the left. You go from a basis that is fixed in A, what I used to call F, to this basis that is fixed in B, what I used to call F prime. And so you put them in this order here, and you get what is CBA. You can also say that this is a rotation matrix of B with respect to A. There are some properties. Again, I'm going to skip a few things unless they're really important, and I'll just give you the results. You're more than welcome to go and prove them, or find in books where these things are proven. For a DCM, these relationships are valid. C transpose times C, it's the same as C transpose and gives you the identity matrix. Also, transposing a DCM is the same as inverting it. Its determinant, it's always 1. And important, this equation here that I am circling with my little hand, this is, you could stop here. This is a differential equation where the entire DCM is derivative in time once, so all these C11, C12, C13, etc., they're all with a dot on top of them, times C itself transpose, it's equal to minus omega x. Omega is the vector, omega on the x-axis, omega on the y-axis, omega on the z-axis of B, and the x represents the fact that you take that vector and you organize it into a skew symmetric matrix. And I invite you to find what that means, which you should know. It's a very simple reorganization of the components 1, 2, and 3 of the vector x, y, and z into so that you form a matrix which is skew symmetric, so zeros on diagonal. But the bottom line is that these could be the end of the story. These are 9 differential equations that give you the time derivative of each of these numbers, these cosines of the direction cosine matrix, that you can absolutely integrate in time. You have to remove the C transpose here by a simple operation, multiply times C here on the right and the same on the other side, you remove it, so you have the differential equations that, given an omega evolution in time, you can integrate and find how those 9 numbers will change, and the evolution of the DCM will tell you how B is changing orientation with respect to A. Now, that is a very inconvenient thing to do. You have 9 differential equations. They are not exactly all independent. In fact, this relationship here gives me 6 independent scalar equations. So one actually starts being tempted about basically trying to find only 3 parameters that may be enough to represent an orientation, and you're already thinking about other angles, of course. That's the first thing. And then, the visualization of how B is oriented with respect to A by looking just at a matrix, it's something that, unless you're a genius, no one can really do. Now, there's a bunch of stuff in these notes that you're more than welcome to read more in details, but I want to cover the high-level view. These are all proper rotations, of course, what we do, so if you ever come up with a DCM that doesn't have determinant of 1 but has -1, there's something wrong. A small note, if you look at the DCM and you look at columns, you will see basically the projection of the bases. Now I'm changing nomenclature again, but these A1, 2, and 3 are the bases of the frame A, and B1, 2, and 3 are the bases of frame B. So the columns will be projection of A1 on the B basis, A2 on the B basis, A3 on the B basis. If I go by rows of the DCM, I have projections of the B basis into A. So first row is B1 projected in A, B2 projected in A for the second row, and so on and so forth. Well, that's only 3 of them. Now, how to use a DCM? First use is what it was introduced for. It's orientation of a frame with respect to another, how B is oriented. Then, if you're given a vector in A, expressed in the A basis, you pre-multiply that by the CBA matrix, and you're given the vector in B. You can easily go back into this structure here and convince yourself of that. So this is CBA. Imagine that you multiply here times the components of a vector that is expressed in A. It will give you the vector in B. And so, remember, we go from right to left. So I'm going from A, I apply the matrix that goes from A to B, and I end up in B. And by transposing CBA, you get CAB. You can do the opposite. Another beauty of the DCMs, and this is my suggestion when I give you a suggestion, define a nominal DCM that points at the moon and then add an additional rotation on top, is that if you have successive rotations, if you take an object and you do one rotation and then you compute its DCM, and then you do another rotation and the next DCM, and so on and so forth, well, the final orientation can be expressed by the product of all these rotations. In other words, if I have DCM that goes from a frame A to B, and then B to C, and then C to D, and so on and so forth, by multiplying in this way, going from, again, left to right with the subscripts, will give you the DCM that goes from A to D. And that's exactly how we build the other angles. Now, skipping all this, in principle, we can use only 3 variables. So here I'm saying go to page 5 of the slides of lecture 4, which means that I'm basically going and showing you this. So if you want to reduce that DCM and basically represent it with 3 parameters, there are several ways of doing it, and one is with other angles. So remember, my goal here is, I know that DCM is the solution. It's 9 variables, 9 differential equations in principle that I can integrate. It's ugly and it's a lot of them, and I don't need 9. And so people try to parameterize the DCM with reduced sets of variables to make it more convenient. Each type of parameterization of the orientation has advantages and disadvantages. Now, with other angles, you basically use what are called principal rotations. As you see in this image, a principal rotation is a single axis rotation. Rotation phi of an angle phi about axis of the first axis of the A basis, or rotation about the y-axis, or rotation about the z-axis. And what these give you are simple matrices of this kind. If you rotate about a single axis x, the first the first component is 1 here, 0, 0, 0, 0. You have cosine and sines down here. So here you're representing how you're going from A to B, or B to A if you transpose this, depends who you call A or B, by a rotation on the x-axis. This is rotation about the y-axis. This is rotation about the z-axis. And you should be really at this point able to recognize them right away, or if I ask you a principal rotation about any axis, you should be able to write it right away because it's always the same story. There is a cosine, cosine, minus sine, and sine, except here there is a minus up here. But really the one is going to be occupying the correct location depending on if you're doing a rotation about the x-axis, it occupies position 1, 1. Y-axis occupies position 2, 2, and the corresponding row and column are always a bunch of zeros. And the same z-axis, then it's going to be in 3, 3. And so other angles basically is just a way to go from the orientation from A to B to the final orientation with 3 successive principal rotations that occur on intermediate axes. The first is about any axis, then the remaining 2 are on the non-used axis. And the most common one that we've seen in astrodynamics as well is the 3, 2, 1 rotation, which is here depicted on the next slide. Let me make this bigger. So you want to represent how this frame B and its basis ended up in this whatever configuration with respect to A. You can always break it into a first rotation about the z-axis. That's why it's called 3, 2, 1. Z-axis, this creates new intermediate x and y. You use the new y, the intermediate y, and rotate about that. It's going to create new intermediate z and x. And then finally, so 3, 2, axis 2, and then 1. The last rotation is about the new x-axis, which is going to be the final x-axis, and so it's going to correspond to B1, and then you obtain with that B2 and B3. And so, since you've done them in this order, you're going to assemble the matrix, the direction cosine matrix that goes from A to B by multiplying the DCMs, the individual DCMs, the ones that I showed you before, except that I called the angles with different names, in this way, C3, C2, C1, because these happen first, then this, then this. So you go from 3 to 1, and you get A to B. And let me go back to my PDF. Basically, the C3 is this one, will look like this. C2 will look like this. C1 will look like this. And it's good stuff. If you multiply them all together, you're going to get this nasty DCM. So I am now representing the DCM, the same quantity that was before a matrix with 9 numbers with only 3 variables. I have 3 angles here, except there's a bunch of sines and cosines, which is not very, very nice, but it's what it is. Now, if you recall, and I'm going fast on this because you should have seen this again in several classes, what happens with other angles? Well, what happens, for example, for a 3, 2, 1 rotation, if the second rotation, for example, it's 0 degrees, it's 90 degrees in this case, you're going to orient this A3 on the plane, or original XY plane, and this A1 is going to point down. So if the second rotation is 90 degrees, your intermediate x-axis, which is the one on which you have to do the last rotation, because it's a 3, 2, 1, is going to be exactly parallel to your initial rotation axis. And so A3 and A1 second are going to be parallel. And what that happens is that you're going to have infinite combinations of this angle and this angle, psi and phi, that can give you the same final orientation. And that is a bad idea. You don't want anything, any representation to basically be not univocal, because it's the example I always give is like saying that your particle is in 3-dimensional Euclidean space, and its position can be represented by 3 values x, y, z. There are 3, 1, 3, but also 4, 2, 5. That is not a good thing to do. You want a ruler that works just in one way, and it's there is a one-to-one association between the actual configuration of the system and the variables you use. In other words, mathematically speaking, if you do that, second rotation is 90 degrees. This is your DCM. with Euler angles. See, psi and phi appear here. So as long as the difference is the same, you can choose any combination of these two. You're going to get the same matrix. So they become associated with the same axis, these two rotations, and these do not represent properly the attitude. It also causes numerical problems. If you look at in the Bongui's book, at the differential equations they give you, the time derivative of these three angles, phi, theta, and psi, as a function of omega and the angles themselves, there is a term at the denominator, which is the cosine of the second angle, theta, that goes to 0. So you do have also numerical problems. So you have infinite combinations of psi and phi that represent the same orientation, and it's not a univocal parameterization. So you can throw it away. This happens with all Euler angles. All 12 possible sequences have singularities. Let me go back to my PDF. I think I have a list of the possible combinations. These are all the things you can do. You can do 1, 2, 3, 3, 1, 2, etc., etc. So these are not symmetric, or there are symmetric ones where the first and last axes are the same. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12 possible combinations. The asymmetric ones will have the singularity on the second axis when that rotation is 90 degrees. The symmetric ones, you can prove it to yourself by just playing with your fingers, or trying to draw a sketch, have the singularity when the second rotation is 0 degrees. So they do have some issues. They do allow you to deal with things with only 3 parameters instead of an entire DCM on 9 variables, but they have the singularity problem. And so the good things about Euler angles, they are, well, easy, quote-unquote easy to visualize. They have a physical meaning. They are angles. We can deal with angles. We can kind of visualize those. We don't like visualizing 9 numbers in a matrix to tell someone how a spacecraft is oriented, right? But the bad things are a lot of them. Singularities, again, you lose meaning of a representation when you hit a singularity, and that also has numerical implications because you divide by 0 somewhere. And then these are trigonometric functions. Spacecraft do not have a lot of computational capabilities, even if things are changing, but processors are not that efficient when they have to do that. And remember that even the most refined of calculators gives you an approximation of a sine over cosine. It is a series expansion. So there are better things to do. And the better things to do are using 4 components instead of 3, 4 variables instead of 3. There is a redundant representation such as quaternions, which are a sub-case of Euler parameters. And then, so you use those to integrate your kinematics equations, and then, which is what you're doing at Simulink with Senny's code. And then, when you really need to visualize things, you can always, with quaternions, go to the DCM and extract a sequence of Euler angles if you want to really visualize something with angles. But at least, numerically speaking, and throughout any type of rotation, no matter if you go, through strange angles or repeated rotations, you're not going to have any problems. Now, quaternions. Here I'm going to skip the math because this is not the point, but we want to understand how they are built. They're based on the Euler eigenaxis rotation theorem, which says that rotating a rigid body about an axis that is fixed in the body and stationary in the inertial frame, the rigid body attitude can be changed from any given orientation to any other orientation. In other words, if you give me an object which is oriented in any particular configuration, doesn't matter, with respect to the ECI, your spacecraft can be oriented in any way with respect to ECI, you can find an axis which is fixed both in the body and in the inertial frame, and you can locate a value of an angle about that axis so that you can obtain that configuration by rotating of an angle alpha, that angle alpha about that axis. Such an axis of rotation whose orientation relative to both the inertial reference frame A and the body B remains unchanged throughout the motion is called the Euler axis or eigenaxis. We don't demonstrate this. It's called eigenaxis because basically it's the same if you represent it in A or in B. So if you apply the DCM C A to B to E, you get E itself. So it's an eigenvector of CBA. Now, all possible sets of variables, there are 4, there are Euler parameters, are composed by the eigenaxis and this axis, E, and an alpha angle. They're just different combinations of these two. Now, I say here that you can skip to page 37 of the notes, and that's exactly what we are going to do. I'm going to define the quaternion and just show what are the the relationships that are important to us. And just remember, the only thing we need to remember is that they are just another way to take the DCM and represent it with less than 9 parameters. All angles are away, but they have the problem of singularity. All quaternions lose the visualization ability a little bit, even though they have some kind of physical meaning, because there is an axis and there is an angle, but it's just very difficult to see it. All angles are easier to visualize. But you can always go back and forth between, among all these representations. So quaternion is defined. This is a definition. Sir Hamilton invented them. You take that axis, which is going to change in time. This all axis changes at any instant in time, as well as the alpha vector. But this angle. But this is how the quaternion that goes from A to B is defined. Is a 3-component vector here given by E that multiplies the sine of alpha over 2, because this is the E vector, if you think about it. E1, E2, E3 is just multiplied by this scalar, which is sine of alpha over 2, and a scalar component, cosine of alpha 2. Seni, I think, gave you the code that has the scalar component as the first one, and then the vector part, which is these 3, E1, 2, and 3 times the sine of alpha over 2. There are actually at the end, but it doesn't matter. It is just a matter of keeping in mind where the scalar is. And so usually it's given by Q, Q1, 2, and 3, and this Q4, that is the scalar part. Its norm is always 1. They are definitely harder than all angles to visualize, but they don't have a physical meaning, but they don't have the singularity problem. Now, without any demonstration, if you have the quaternions and you want to find the DCM, this is your relationship. Just memorize this if you want or not. It's in the books, it's in the Bungwe's book. You can just keep this in mind. If you ever need to go from a quaternion to DCM, this is what you do. The vice versa is the following. If you're given the DCM, this is just another way of writing it. If you're given the DCM, so you have the components of this matrix as we discussed them before, and you want to go to the quaternion, the scalar component is given by this expression, 1 over 2, 1 plus C11, C1, C22 plus C33 under the square root, and the vector part, Q1, 2, and 3 are given by this other relationship. That's the end of the story. And so imagine what you can do with this. If you have a quaternion, you go to the DCM. Once you have the DCM, once it's computed, it's a bunch of numbers. It's 9 numbers. So you can go back here and let's see, where is that given? And basically, think about that DCM in terms of all angles. So you can translate the DCM back into all angles if you want. You can go back and forth. You can do whatever you want. Skip these pages, are really not really required. Go to 37 to the definition of quaternion directly. I'm sorry, 38 should be 38. Yeah. So 2 successive rotations. As we said, it's the multiplication of the DCMs. There is a way to do it with quaternions, which is called quaternion product. It's not just taking and multiplying one element to the other with the other. It is this expression here, which I prefer expressed in this manner. So if you have a quaternion Q1 and a quaternion Q prime and Q second, the resultant quaternion, that is the sequence of the 2 rotations, can be expressed in this matrix times a vector form. There is no trigonometry that is involved, which is nice. We don't like sines and cosines. There is a suggestion you to solve the book from the Bungwe if you want, and a bunch of other properties that we don't really need to necessarily explore in details. Again, the goal of these is just giving you an overview. But there is no singularities here. They are efficient for computer calculations. It's what it's used. The most important thing for this class is what people use on spacecraft. So you're not using something because Seni or I like it particularly. It's because that's what people do for spacecraft. Keep in mind then that basically you can always go, forget about all this stuff. So basically you can just, go with my definition of quaternion. The differential equations that give you Q1, 2, and 3, and 4 dot are given in the code that Seni gave you, and they are in the Bungwe. But the bottom line is that they are defined this way, and that you can always compute the DCM. From any representation that you use, all angles, quaternions, doesn't matter. You can go to the DCM. The DCM is the way to represent orientation. It's just not very convenient. The same as all angles. It's an attempt to be more convenient, but it has limitations. So quaternions are really something in between the DCM and all angles. They're not visualizable, but they're definitely better than having singularities. And when you need to visualize something, you can always go back to the DCM, and from the DCM you can extract your Euler angles. I hope this clarifies a little more. Let me see if there's anything else that I want to add. I don't believe so. Really, keep in mind that, again, you can go from one set to another without any problems, without any issues. I don't have here the equations. I don't know if I have them anywhere that allow you to go from the DCM to Euler angles, but they are absolutely in the Bongui's book. I thought I had them in these notes. Let me just quickly go through them one last time. I don't believe so, but they are quite easy to do. In other words, what you do is, this is your DCM expressed by Euler angles. Well, once you know that this is how it looks like, well, the sine of theta allows you to extract theta from the component that is up here at position 1, 3. Once you have the sine of theta, for example, you can take this one and extract phi, and so on and so forth. So you can figure out what the Euler angles are by just looking at key elements, the simplest ones in this DCM. So remember, DCM is a bunch of numbers. It's 9 numbers. It's just that I choose to represent it this way if I use Euler angles, so I can give those 3 angles, sequence 3 to 1 in this case, a meaning through the DCM. And the same story is down here for the quaternions. Once I define quaternions, I know that each of these 9 numbers in the DCM can be expressed by a combination of the quaternions, and this is how I extract the quaternions themselves. Q4, the scalar part, and the vector part. And if there's any questions, we can talk more in class. Thank you.